Hello and welcome to 11.7. It's still integration, year 13 of Edexcel's A-level course, or year 2, the second year of A-level essentially. And this time we're going to have a look at a particular method of integration which relies on splitting into partial fractions. So partial fractions are something you should have seen before because it's done in chapter 1. And so what I'm going to try to do here is to give the partial fractions as the warm-up, and then how to use that warm-up to then integrate as the main bit of the lesson. So as long as we can remember how to do partial fractions more or less, we'll be set to go and okay to understand this main topic in this very video. So here's the warm-up questions. As I mentioned, I've included 3 here which are to get you just splitting into partial fractions once again, and then question 2 and question 3 are introducing different ways essentially of how we could also split things into partial fractions. Okay, so assuming you've had a go at those questions, let's see how you've done by looking at the solutions together, starting of course with warm-up question 1. So question 1, we're expressing the following as partial fractions. So the first one, we've got x minus 5 all over x plus 1, x minus 2. So what we're going to do here is set it out by saying x minus 5 over x plus 1 multiplied by x minus 2 can be written as a product, so the sum of 2 different fractions, some constant a over x plus 1, the first factor, plus another constant b over the second factor in the denominator, x minus 2. So now we just need to remember what we need to do next. Now multiply both sides of this relation by x plus 1, x minus 2 to clear out the denominator from this side. And after we do that, we'd arrive at the next step, which is we just have x minus 5 equals a multiplied by x minus 2 plus b multiplied by x plus 1. Because when we multiply a over x plus 1 by this whole thing, the x plus 1s will cancel, just leaving us with the x minus 2. And similarly for the x plus 1 factor with this fraction involving b. Now we can just pick suitable values for x to eliminate either one of the two brackets, so we can focus on working out either a or b. So first of all, what we could choose to do is we could sub in that x is equal to 2. This will make this bracket vanish. 2 minus 5 is then minus 3. Then we get minus 3 equals 2 plus 1, 3 b's. Therefore, b must be equal to negative 1. Now if we were to sub in x being negative 1, what we get next would be that minus 6 equals minus 3 multiplied by a. Dividing 3 by negative 3 therefore tells us that in this case a would be equal to 2. Piecing that together, we can therefore see that x minus 5 all over x plus 1, x minus 2 is the same as 2 over x plus 1 minus 1 over x minus 2 when written in partial fractions. Part B is a similar idea, but we need to remember for part B what we need to do. We have a repeated factor in the denominator. In this case, we have a repeated factor, which is x minus 2 all squared. So we account for that by writing out and setting it out as follows. So we here say that 8x squared minus 19x plus 1 over 2x plus 1 multiplied by x minus 2 all squared is a over 2x plus 1 plus some constant over x minus 2, without this bracket being multiplied to the second power, and then plus c to the power of x minus 2 squared, to account for the fact that we might just have something to do with x minus 2 squared without the x minus 2 being a hidden factor. So we need to put both the single power of a bracket and all the way up to whatever the highest power it goes to. So for example, if this were x minus 2 cubed, we would have done x minus 2 squared, then a third bracket, x minus 2 cubed. Anyway, now, the setup is similar to what we did last time. We're going to multiply both sides by the denominator of the initial fraction. So multiplying by 2x plus 1 and x minus 2 squared is going to give us the following. We're going to have 8x squared minus 19x plus 1 equals a multiplied by x minus 2 squared plus b multiplied by 2x plus 1 x minus 2 plus c multiplied by 2x plus 1. Now we just need to carefully consider which of the 3 numbers we can substitute in for x will allow for cancellations for a, b or c, so we can focus on just working out one constant at one time. I'm suggesting we pick x equals 2 first. If we sub x equals 2 into this bit here, we're going to get 32 minus 38 plus 1, which gives minus 5. And then if x equals 2, this bracket will become 0. This b term here will be 0 as well, because that bracket will become 0. We're just going to get 2 times 2 plus 1, 5 lots of c. So minus 5 is 5 c's, therefore c has to be equal to minus 1. Next, we could choose to substitute minus a half for x. If you try this on your class whiz, on this side, we're going to get 12 and a half. I've put it as a decimal here. You could put it as 25 over 2 if you wanted, doesn't matter. 12.5, and then the b terms and c terms will cancel, because the 2x plus 1 bracket will become 0 when we input x being minus a half into them. We'll just get that we've got a multiplied by minus 2.5 squared, 6.25a. So if we just divide both sides of this now by 6.25, we can clearly see a's got to be 2. To work out b, there are now a few options, but I'd suggest just substituting in any value pretty much for x, so that either bracket here for b isn't eliminated. So as long as we just sub in something other than 2 or minus a half. Normally I think the easiest one, if it's not taken already, is to just use subbing in x being equal to 0. So if I do that here, and sub in x being equal to 0, the left hand side is just going to obviously become 1, and we're going to get that 1 equals a times by 4. A is 2, so we're going to get 2 times 4, plus b multiplied by 1 times minus 2, which is going to get minus 2b, and then we're going to have c multiplied by 1, which therefore is just going to be just minus 1, because c is minus 1. So if then we knit this up and solve, first of all we're going to get that 2 times 4 is 8, minus 1 gives us 7, so 1 equals 7 minus 2b, so it must be the case that b is 3. Putting these facts together for a, b and c, we've therefore got our partial fraction decomposition. So finally, we can just say that 8x squared minus 19x plus 1 all over 2x plus 1 brackets x minus 2 squared equals 2 over 2x plus 1 plus 3 over x minus 2 minus 1 all over x minus 2 squared. Finally, one part c, we need to spot for this one, which is 2 over 1 minus x squared, that the denominator is in itself a difference of 2 squares. So we need to rewrite this, first of all, as 2 over 1 plus x brackets 1 minus x, in order to then split it into the partial fraction pair a over 1 plus x plus b over 1 minus x. In the same way as before, if we just multiply through this relation by both 1 plus x and 1 minus x, we get the next step, which will be that 2 equals a brackets 1 minus x plus b brackets 1 plus x. First of all, I'm going to take that x can be equal to 1. If I sub x being equal to 1, this thing here to do with a will vanish. I'm just going to get 2 equals b times 2. So if 2 equals 2b, obviously b must be equal to 1. Now if I sub in that x is going to be equal to minus 1, this bracket will now vanish, and next we'll have that 2 equals a multiplied by 1 minus minus 1, which is 2. In other words, 2 equals 2a, so a must also be equal to 1. So therefore the partial fraction decomposition of 2 over 1 minus x squared is 1 over 1 plus x plus 1 over 1 minus x. Question 2, what we need to do here is to use a method of polynomial division to express f of x, this fraction, which is basically 9x squared minus 3x plus 2 all over 9x squared minus 4, we need it in this form here, where a, b and c are integers to be found. So if we set out our polynomial division question like this, so 9x squared minus 4, what we're dividing goes at the front, and then a fraction line here, with what we're dividing going underneath, so 9x squared minus 3x plus 2. So the first thing we do is we take 9x squared and divide by the 9x squared above it. So we take the highest power of x divided by the highest power of x here. This term divided by this term, and obviously that's just going to give us, in this case, 1. So we write 1 here, the next step we do 1 multiplied by x squared minus 4. 1 multiplied by 9x squared is 9x squared. 1 multiplied by negative 4 gives negative 4, which I'm going to put underneath a constant 2, so the constants line up, as do the x's and the x squared terms. What we next need to do is to subtract these lines, one from the other. So 9x squared take 9x squared cancels. We have a negative 3x here, which essentially we're taking away 0 from it, so we're going to get negative 3x down here. And then 2 minus minus 4 becomes 2 plus 4, which is 6. So this is the remainder, because we can't go again. Because this power of x is less than the power of trying to divide, we're done, and this is therefore what's left. So therefore, we can say that 9x squared minus 3x plus 2 all over 9x squared minus 4 equals the quotient, which is 1, then plus the remainder. So remainder here is minus 3x plus 6. So we're going to add minus 3x plus 6 over the original denominator. If you wanted to here, you could have also written 6 minus 3x, I suppose, but I'm just trying to stress it's in the form a, b, and c. So 1 minus 3 and 6 for a, b, and c respectively. Before I begin properly explaining question 3, question 3 I've set up to be very similar to question 2, essentially where the numerator and the denominator are of the same degree. Both of them have the same highest power of x, in this case both degree 2. So in warm-up question 2, I showed you how we could use polynomial division to express this in partial fractions. This warm-up 3, I can show you how this can actually be rearranged into partial fraction form by trying to manipulate it so that the denominator appears in the numerator. So it's self-explanatory really by taking part A as it comes. So we're going to use the substitution u equals 2x squared minus 2 to show that this whole thing can be expressed in this form here. So we're going to say that g of x, obviously we've got mu on the bottom, so u on the bottom, because u is 2x squared minus 2. And this here is essentially something to do with 4u, because we've got an 8x squared. So if I write 4u first, we can then think about how to adjust this. Well, 4u is going to be 8x squared minus 8. So I've got 4u so far, which is 8x squared minus 8. I want to end up with plus 1. So to go from minus 8 to the positive 1, which I need, I'll need to, of course, add on 9. And I've got no x terms at all. So the only way I'm going to get this negative 5x is by inputting minus 5x here. So just as with any fraction, algebraic or otherwise, I can split this into two different fractions. So I can say this is the same as 4u over u. Then I can say it's the same as plus minus 5x plus 9 all over u. So this is part A. So part A, g of x I can write as 4u minus 5x plus 9 over u. And for part B, I'm just taking this one step further. 4u divided by u, obviously the u's will cancel on the top and the bottom, so I'm just going to get 4 plus minus 5x plus 9, oops, wrong colour, sorry, plus minus 5x plus 9 all over u, which we of course will just put back in its original form, 2x squared minus 2. So now we've done warm-up question 1, 2 and 3, let's have a look how this relates to integration. Integration using partial fractions is what I'm trying to get at. So, as we've seen in Chapter 1 of the Year 2 textbook, algebraic fractions involving a quotient comprised of polynomial products can be expressed as partial fractions. An algebraic function written in terms of partial fractions is simpler to integrate, and therefore a primary application of partial fractions is as a tool for finding integrals. So the hope is that that warm-up we've set up, questions 1, 2 and 3, has reminded you of how to use and apply partial fractions, how to split one fraction into many. Usually, integration using partial fractions produces expressions in terms of the natural logarithm. So essentially, you'll therefore need to be really confident in your knowledge and use of the laws of logarithms beforehand. So know about the addition of logs, subtraction of logs, log to certain power, exponential and inverses and all that stuff. So be comfortable with the logs, and in particular the natural log ln. So let's have a look at worked example 1. So don't worry if these look a bit familiar, it's because they are. We're going to use partial fractions to evaluate these integrals. So a, b and c formed part of a warm-up. For warm-up we're just simply splitting these into partial fractions. And so, assuming we now know how to use partial fractions again, we're just going to get onto the primary application of how these are now transformed using partial fractions into integrals which are easier to solve. So to recap from warm-up question 1, here's what we had for a, b and c if we split the integrands into partial fractions. So for a, we had that it becomes 2 over x plus 1 minus 1 over x minus 2. For b, we had this as the following, and c, we had this in partial fractions as well. Sadly, there's no more space for us to write anything else, is there? So, assuming that's a given, or imagining that we've done that and that's okay, let's just focus now on the fact we've got to this midpoint, we've got to the fraction expressed as partial fractions, and let's see if we can integrate from there. So just clearing out some space, let's just focus on these results here at the bottom, which are now going to shove to the top. So, first of all, the integral of x minus 5 all over x plus 1, x minus 2. So, for this one, essentially what we've done here is we've transformed this into this thing here. And so now we can just say that we're integrating something simpler, which is actually the case. We're now integrating this instead. I'm going to put the 2 on the outside. So I'm going to say it's 2, and then I'm going to say it's 1 lot of x plus 1 dx, and then I'm going to put the minus 1, then the integral 1 over x minus 2 dx there. Just by doing it this way, it's just an easier way of seeing that these are going to become both in terms of natural logarithms. Because if the derivatives of each of the denominators, derivative of x plus 1 goes to just 1, as does the derivative of x minus 2. So we're going to get the natural log of x plus 1 and the natural log of x minus 2 secondly as well. So this is going to become now 2 lots of the natural log of the modulus of x plus 1 minus 1 lot of the natural log of mod of x minus 2, and then of course plus c, where c is some constant. Then I can write this a bit simpler using the laws of logs, so I can set the same as ln mod of x plus 1 squared, bring back 2 to the front using it as a power, divide by x minus 2, all plus c. And so that's absolutely fine. In brackets, just to go one step further, sometimes a question might ask you to write it with a constant somewhere in here. So if I think of c being rewritten as equal to natural log of some other constant k, But I can combine this into this natural log as well. So I could have also said as an alternative answer, just as good, k lots of x plus 1 squared all over x minus 2. That's just a different option we could have used. This one here, part B. So this time, this integral, we've transformed into this, where we've got the constants 2, 3, and negative 1. So again, we're going to have integrals in terms of a natural log once again. So here, 2 is the derivative of 2x plus 1. So we're going to leave that within the integral. So integral of 2 over 2x plus 1 dx. This 3 that I'm going to take to the outside, plus 3 lots of the integral of 1 over x minus 2 with respect to x. And now this minus 1 over x minus 2 all squared, this is not going to actually integrate to anything to do with the natural logarithms. So what I'm going to suggest we do for this final piece is to write it as minus the integral, and then to rewrite this as a index rather than as a fraction. And so I'm going to suggest rewrite this as x minus 2 to the power minus 2 with respect to x. So now we can integrate these individually. So the integral of this with respect to x is going to be ln mod 2x plus 1. The integral of this with respect to x is going to be plus 3 lots of a natural log of x minus 2, the mod of all that. And this here, we could either use a u sub or just essentially by inspection when we get confident enough. If we do a u sub, for example, where u is x minus 2, the power minus 2 would increase to a minus 1, then we'd divide by that u minus 1. So this would become minus x minus 2 to the negative 1. But because it's already a minus on the outside of the integral, we're actually going to get plus 1 lot of x minus 2 to the minus 1. If I'll just write that in a better way, I can rewrite it afterwards. So it's going to become x minus 2 to the minus 1 plus some c. So now we can neaten this up somewhat. So I'm going to write this as ln. This time what we have is ln of one thing plus ln of something else too. So it can be combined as a product. So it's going to be ln 2x plus 1 multiplied by x minus 2 cubed. This here I can rewrite in a more natural looking way. I can put it as 1 over x minus 2 plus c. I'm not going to bother this time writing again any different forms. The examiner will make it clear to you which form they want it in. So for now that will do us. Part C of this, to now integrate this. Similar idea to last time, of course. We've just expressed this integral here in terms of partial fractions there. So instead we're going to integrate using this result instead. So it's going to become next the integral of 1 over 1 plus x. This actually is the easiest one. Plus the integral of 1 over 1 minus x with respect to x. Just a final thought here though. If we differentiate 1 minus x, we get negative 1. But here we've got positive 1. So I'm going to adjust this 1 to a negative 1 by changing that plus on the outside of the integral to a minus. So by making this cheeky little adjustment, minus and minus still becomes plus 1 essentially. But now because the numerator is the derivative of the denominator, it's just easier to see and spot that we're going to get ln of 1 minus x when we integrate. So overall, from this one, we get ln mod 1 plus x minus ln mod 1 minus x plus c, which we can now finally write in the simplest form. So we can now write this as ln mod 1 plus x all over 1 minus x, all plus c. And what I'll do actually, I'll write this in a second way as well, similar to part A. If I were to think c, the constant in its own right, I could rewrite this as being ln k. I could also include this within this natural log 2. So also, it could be expressed as ln some multiple k of 1 plus x all over 1 minus x. So that's expressing and integrating using partial fractions part 1, if you like. But what about different fractions which we might need to use partial fractions to integrate? So, what about when the degree of the numerator of a polynomial is equal to the degree of the denominator? So when that happens, if you've got something, for example, squared as the numerator and the denominator is also something squared, or they're both cubed on the numerator and the denominator, we need to take extra care. So if the degree of the numerator and denominator are equal for some f of x, we first must rewrite the function as a constant term plus as a fraction that can then be decomposed into partial fractions after. There's a few approaches we can use. So any one of the following approaches is valid. So approach 1, we can use polynomial division to express the function as a constant term and a fraction. So see Warm-Up question 2 for how we did that particular method. So using this idea here, we get a constant term, then a fraction, and then that fraction, which in itself we might need to split into partial fractions again. So that's approach 1. I'm going to show you how approach 1 works, and I'm going to show you how approach 2 works as well. Approach 2, what we could do is we can rewrite the numerator in terms of the denominator, plus or minus other terms to cancel out and to balance, and then split the fraction into a constant and a new fraction. See Warm-Up question 3 for how we did that in practice. I'll show you again here. And finally, approach number 3, set f of x as some constant term a, and then plus some constant over the first linear factor, plus some constant over the first linear factor, and so on. And then compare the coefficients and rearrange as necessary, and substitute as values for x, to then work out what these constants a, b, c, d, etc. are. So this bit here works and is much easier to see in practice. All it means is once you've got your constant term, to rewrite the rest of it in terms of its individual factors if it's already factorized, or this might be, for example, the original denominator, in which case this term here is a polynomial with degree 1 less than the denominator. Again, in practice it's much easier to see than just the theory. On that note, let's put it into practice. So worked example 2, what we're going to do here is we're going to find the integral of 8x squared minus 5x plus 1 all over 2x squared minus 2 with respect to x. So we're going to do this showing these 3 different approaches. So the first goal is to split into partial fractions. So before we can actually integrate it, our first goal, we need to split it into partial fractions first. So approach 1, 2, and 3. So approach 1, algebraic division. So here's how we set it out. 2x squared minus 2 into 8x squared minus 5x plus 1. Our first step is just to see how many times does 8x squared, how many times does 2x squared rather, fit into 8x squared. That's 4 times. Now we do 4 multiplied by 2x squared minus 2, which gives 8x squared minus 8. We now need to subtract one line from the other, and so when we do that, what we're now going to get is just minus 5x, because that minus 5x we're subtracting nothing from below it, minus 9, because 1 minus minus 8 is positive 9, and the 8x squareds cancel. This is now our remainder, because this power of x is less than the power of x here, so we can't go on. So therefore, 8x squared minus 5x plus 1 all over 2x squared minus 2 equals a constant term 4 plus this fraction. Now though, we've got this problem of having this fraction, which now we need to express in partial fractions yet again. So we've done one step, now we need to finish off the job. So this time, what we need to spot is this fraction has a difference of 2 squares in the denominator. If we factorize out the 2, we get 2 lots of x squared minus 1, which then becomes 2 lots of x plus 1, x minus 1. We can now split this into partial fractions like so, by calling it equal to some constant a over 2 lots of x plus 1 plus some constant b over x minus 1. Now following the similar procedure, multiply both bits by 2 lots of x plus 1, x minus 1. Alternatively, you can see this as multiplying both sides by the 2x squared minus 2 without it being factorised. We'd get minus 5x plus 9 on the left equals a brackets x minus 1 on the right, because of 2 brackets x plus 1 cancels here and here. On this side, though, we're going to get 2 lots of x plus 1 multiplied by b, because only the x minus 1 part will cancel, so we're still going to be multiplying b by the 2 and the x plus 1. Now we just need to think about what values of x to input to work out a and b. So if I input first of all x being 1, we're going to get on this side 4 equals 2b times by 1 plus 1, 2 on the other side. The a bracket will cancel. Essentially 4 equals 4b, so b must equal 1. Next, if we substitute x being minus 1, the left-hand side is going to become minus 5 times minus 1, positive 5 plus 9, which is 14, and we're going to get negative 2a, because minus 1 minus another 1 is minus 2, and the b bracket will cancel. And so dividing both sides by minus 2, we see that a has to be equal to negative 7. Now we know that a is negative 7 and b is 1, and we know that the constant term to begin was 4. We've now successfully decomposed this into partial fractions completely. So for final step, just write what we know. Therefore, 8x squared minus 5x plus 1 all over 2x squared minus 2 is the same as 4 plus minus 7 over 2 x plus 1 plus 1 over x minus 1. Approach 2 is the same as what we saw in the warm-up. So just to show you again very briefly, spot that 8x squared minus 5x plus 1 can be rewritten as some multiple of 2x squared minus 2 plus or minus other terms to balance after. Importantly, the x squared term is 4 times big on the top, so multiply the 2x squared minus 2 by 4. So if I do that, 4 lots of 2x squared minus 2 is 8x squared minus 8. So I'd need the minus 5x still, and to go from minus 8 to plus 1, I need the plus 9 in as well. So by rebalancing, I then need to input this myself. Then splitting into separate fractions, I now have this, because the numerator can cancel with the denominator. The first fraction we can cancel, so it just becomes 4. And then, of course, we have this minus 5x plus 9 over 2x squared minus 2 to contend with. At this stage, we're now at exactly the same stage as we were using approach 1. So now after this point, we just do exactly the same as before. So I'm not going to repeat myself again. Then it's the same as before, this approach here, as in we saw in approach 1. Approach 3 allows us to actually split fully into partial fractions in one move, rather than having to do the constant term plus another fraction, then going again with a second fraction. So we can do it in one step, although the one step is slightly longer as a step. But because it essentially feels more like one move than two, approach 3 is my favourite personally. So what we do for approach 2 is, because we need to know first of all if the numerator is the same degree as the denominator, when we do one divided by the other, we're going to get some constant. So we need to know there's going to be some constant term, then plus it's going to be the rest split into partial fractions. And what we could do here first of all is actually split this by factorising the denominator. So for approach 3, if we factorise the denominator, which doesn't have much use in approach 1 or 2, but here now it does, we get this form here. So we can split it first of all into partial fractions already. So we can rewrite this as some constant term a, knowing that we can do that if the degree of the numerator and denominator is the same. We need that knowledge to be comfortable using this method. And then, because the first linear factor on the denominator is 2 lots of x plus 1, write that, where b is some constant to be found. And that's a second factor on the denominator, so then put plus c over x minus 1. So now it becomes exactly the same as approach 1, just with one more constant to find. So first of all, if we multiply everything by this denominator, so by 2x squared minus 2, or equivalently 2 lots of x plus 1, x minus 1, we'd arrive at this step. 8x squared minus 5x plus 1 equals a multiplied by 2x squared minus 2 plus b multiplied by x minus 1 plus 2 lots of c multiplied by x plus 1. So now we can just tactically look, compare and contrast to work out what each of a, b and c are. The first thing I'm tempted to do is to just substitute in x being equal to 1, because if I do that, the a and b brackets will cancel straight away, and I can work out what this c is over here. So when x is equal to 1, the left just becomes 4, the right just becomes 2c times 2. Therefore, c must be equal to 1, because this means 4 equals 4c. The next thing, I'm drawn to the x squared terms here. I need 8x squared. The only way I can get x squared terms is by this 2x squared multiplied by the a. And so 2a x squareds has to be the same as 8x squareds. So by comparing those terms, we can spot that 8, the coefficient of x squared here, must be the same as 2a, the coefficient of the x squared over here. So if 8 equals 2a, it's got to be that a is 4. Next, what we could do is we could sub in simply that x is equal to 0. So if we do that, the left is going to become just 1. Then we get a multiplied by negative 2 minus b plus 2 lots of c. So if we input what we know, knowing that a is 4, we get that 1 equals negative 8 minus b, and because c is 1, plus 2c just becomes plus 2. So 1 equals minus 6 minus b, stands to reason that b has to be negative 7. Putting all that together like we did using the previous approaches, because a is 4, b is negative 7 and c is 1, we get the same result anyway. So putting that all together, we have that 8x squared minus 5x plus 1 all over 2x squared minus 2 is the same as 4 plus minus 7 over 2 lots of x plus 1 plus 1 over x minus 1. So using whichever approach we want, now we've completed goal A and got it into partial fractions, we can now say goodbye to that and think about the final goal, goal B, actually integrating it, using the fact now that 8x squared minus 5x plus 1 over 2x squared minus 2 actually can be written in this form here. And that's exactly what we're going to do. So, because this is how we can rewrite that, then let's do so. So we can transform this integral into being the integral of this here, which I might as well just be consistent and do colour-coded as well. So it's going to be the same as the integral of 4 lots of whatever with respect to x, so same as equal to 4 lots dx. This here, because we've got an x plus 1 at the bottom, I'm going to just rewrite this as minus 7 over 2, then the integral of just 1 lot of x plus 1 in brackets like so. So inside the integral like so, dx. And then finally this one here, just 1 lot of 1 over x minus 1 dx. So step by step, this here will just give us 4x. Over here I'm going to get minus 7 over 2 ln mod x plus 1, and over here plus just ln mod x minus 1 plus c. So if I want to neaten this up slightly, I can do. I'll leave it like this for now though, because that is a valid solution. But what I could do, just to show off, or if the examiner needed me to, shouldn't do things just to show off, of course, I could say it's the same as writing this as e in terms of a natural logarithm. I could say it's the same as ln e to the 4x. I can put c as ln k. Leave the others as they are for now. And rewrite c as ln k. I could even, if I wanted to, write this as ln of the modulus. I've got ln k and ln e to the 4x. And also I'm adding ln x minus 1. So this plus ln k plus ln e to the 4x, I can write all as a product. So I'm going to write this as I'm going to write this as k e to the 4x multiplied by x minus 1 and then this bit's minus, so I'm going to do it as x plus 1 all to the power of 7 over 2. So that's all in terms of a natural logarithm. So that's an example of if we need to integrate something where we need to do partial fractions and the numerator is the same degree as the denominator. Now the next part's very rare, but I thought I'd mention it anyway. What if we have a case where the numerator is of greater degree than the denominator? Well, when the degree of the numerator of a polynomial is greater than the degree of the denominator, sorry, tripping over my words, we can either use polynomial division as per approach 1 before, or we can use the fact that when we take f of x and divide it by some other polynomial g of x and decompose it into partial fractions, the degree of the resulting polynomial r capital X, deg r, is the same as deg f minus deg g. I'll call this approach 4, just because I've called the other ones 1, 2 and 3, and I'm lacking imagination these days. This degree business is easier in practice. All it means is, if the degree of the numerator is at least the degree of the denominator, we'll have a resultant polynomial r of x, where r of x could just be a constant term if the degree of a polynomial is the same in the numerator and denominator. But as some examples, this one the degree is 3 on the numerator, this one here would be degree 2. So 3 minus 2 gives us degree 1. So we'd have a linear expression first, which we can call ax plus b. You could call it mx plus c if you really wanted to, as in y equals mx plus c. Then we'd have these other factors on the numerator expressed in partial fractions already, like so. This one here, the top one's degree 4, the bottom polynomial's degree 2. 4 subtract 2 is 2. That means the resultant polynomial r of x would have degree 2. Hence we've got a generalized algebraic function here, ax squared, bx and c, with a, b and c ready to be populated by comparing coefficients and so on. So that's the general procedure, how it works. So let's go from the general to the specific. Let's try one where we're actually going to use definite limits as well. So, worked example 3. Calculate the integral from 0 up to 2 of 4x cubed minus 12x squared minus 22x minus 3 all over 4 minus x brackets 2x plus 1. This time we're told how to write our answer. So give your answer in the form a ln b minus c, where a, b and c are rational constants to be determined. So this time approach 4 is so much better than using algebraic division. I'll show you very briefly algebraic division after, but it's, in my opinion, not worth even going there. So, like before, goal A, first of all, this needs to be split into partial fractions. I'm going to focus on approach 4. Approach 1, the algebraic division, I'll show briefly, but like I say, it's barely worth mentioning. So, approach 4. Write the fraction as the following. This is degree 3. This is a quadratic which has been factorized. 3 minus 2 is 1, so we need a linear term first here, a linear expression, ax plus b, and then we can go into the partial fractions afterwards. Now if we multiply both sides by 4 minus x 2x plus 1, we get that 4x cubed minus 12x squared minus 22x minus 3 must be ax, followed by these brackets, plus b, brackets 4 minus x, brackets 2x plus 1, plus c, brackets 2x plus 1, plus d, brackets 4 minus x. I would suggest comparing x cubed terms first, because x cubed terms can only come from this term here, which is to do with a. So we need 4 lots of x cubed. The x cubed expansion here, we have 2x times minus x minus 2x squared times x minus 2x cubed times a. So we've got minus 2a x cubed, which needs to equal 4x cubed. So because 4x cubed needs to equal minus 2a x cubed, oops, that's a mistake, I should say x cubed. Therefore, we can say that a has to equal minus 2, because minus 2 times minus 2 gets it to match with the 4 that it needs to be. So a is 2. Looking at next, what we could sub if you wanted is x being equal to 4. That gets rid of the a and the b and the d, so we can just focus on c. So when x is equal to 4, trying on your calculator, over here this just reduces to negative 27. The c bracket becomes 2 times 4 plus 1, which is 9, so this becomes 9 times c. If minus 27 is 9c, c's got to be negative 3. Next, we could substitute x being equal to negative a half. By doing that, the a brackets, the b brackets, and the c brackets cancel, leaving us able to find just d. So using the class whiz, this side becomes 4.5, or 9 over 2, and the d bracket, 4 minus a half, gives us 4.5 as well, or 9 over 2. So 9 over 2 equals 9 over 2 times d, so it must be that d is just simply equal to 1. Now we need to find b. We can sub in whatever we want to, and then just work out from there. So if in doubt, just sub in x being equal to 0. When we do that, we're going to get negative 3 equals, the a term is going to vanish, by the way, because a times 0 makes this all disappear. We're going to get b multiplied by 4 times 1, so we're going to get 4b. C is going to become c times 1, which will just be minus 3. And d is going to be multiplied by 4, so it's going to become 4 times 1, because d is 1. So if we neaten this up slightly and solve, we can work out that b's got to be equal to negative 1. So now we know what a, b, c, and d are. We can populate this to express this initial fraction in partial fractions, and then we can go ahead and actually integrate the beast. So that's what it is in terms of partial fractions. If you really wanted to use algebraic divisions, you could, I suppose. Here's how you do it generally speaking. You'd have to first of all expand these brackets, so already you're going out of your way to use this approach. But 4 minus x, brackets 2x plus 1, equals this. We can then do the algebraic division as follows. What you would have got is a quotient of minus 2x minus 1 and a remainder of 7x plus 1. So therefore you could say that the original fraction can be written as minus 2x minus 1 plus this remainder all over 4 minus x, brackets 2x plus 1. You then need to do partial fractions again on this pink fraction here. So then partial fractions again, and then I'm not even going to show you, but assuming you want to have a go at it, which you can, you should still get this same result. Minus 2x minus 1, then minus 3 over 4 minus x, plus 1 over 2x plus 1. So now we've used a suitable approach to get it into this form. I'm hoping you prefer approach 4, to be honest. We can now go for goal B and integrate. So now we're going to integrate it, using this result here, that this thing can be written as this thing. So I'm going to use that result because, to be honest, why wouldn't we? So, using this instead of that means that we can transform this integral. This time, we're told it needs to be in this form as well. Some multiple of a natural log of a constant minus c. So this is equal to the integral from 2 to 0 of minus 2x dx minus the integral of 1 dx from 2 to 0. And then the next, I'm going to write this here as being plus 3. So if I call this here, first of all, plus 3, then the integral minus 1 over 4 minus x dx. Doing it this way because now the derivative of 4 minus x is minus 1, which is on the numerator. And so by just balancing it out like this, rewriting minus 3 as 3 times minus 1, it's just easy to see what this will integrate to. Then I'm going to have plus 1 lot. In fact, there, this here, the derivative of 2x plus 1 would be 2. But here on this fraction, I've only got a 1. So I'm going to factorise out this time a half. Then say it goes from 2 to 0 of 2 lots of 2x plus 1 dx. So now, it's all between 2 and 0. Minus 2x integrated, that'll become minus x squared. Minus 1 will integrate to negative x. This here will give me plus 3 lots, natural log mod 4 minus x. And this here will be half natural log mod 2x plus 1. In between the limits of 2 and 0. So, the upper limit of 2. So, when x is 2, minus x squared will give minus 4. Minus x becomes minus 2. Then I get plus 3 ln. This time, this is going to become ln of 4 minus 2, which is just 2. Then plus half ln. 2 times 2 plus 1, which is 5. So half ln 5. Then minus off when I get the lower limit of 0 substituted in. Minus x squared minus x, that just becomes 0. I'm still going to get 3 lots ln 4. And this bit will become half ln of just 1. Now, ln 1, well, log to any base of 1 is 0, so this here we don't need to even worry about. What we do need to do, though, is to rewrite these in more suitable terms. So, I'm going to get here minus 4 minus 2, that's going to give minus 6. 3 lots of ln 2, I'm going to write as ln 8, plus half ln 5. Now, minus 3 ln 4, I'm going to call 3 ln 4 ln 64. Just make a bit more space. So now I'm almost done, to be fair. What I'm going to suggest we do here is just manipulate it slightly. I want it all as a single logarithm, not in terms of half any logs. I can get them all from half logs into full ones by doubling it through. But you can't obviously just multiply them by 2 because then it will change its value. So what I'm going to suggest we do here is just factorise out a half and then double everything on the inside of the brackets. So I'm going to give myself 2 lots of ln 8. Half ln 5, I can say it's just now ln 5. Don't know if I've even wrote there. ln 5. Then this will become minus 2 lots of ln 64. Sorry, just, yeah, minus 2 lots of ln 64 rather. then of course a minus 12. So this can obviously be neatened up ever so slightly. So this is going to give half. Now, 2 lots of ln8, that's the same as ln64. And so, if I just write this as ln64, just to be very clear what we're doing, plus ln5 minus 2 lots of ln64 minus 12. Well, ln64 minus ln64, just to expand this out for a minute, I'm going to have half of ln. So I'm going to have positive ln5, so I'm going to have the ln5 on the top, and it's half of all this, so it's 5 on the top. ln64 minus 2 lots of ln64 means it's minus 1 lot of ln64. So I can put the 64 on the bottom there. Then half of minus 12, I can just rewrite as minus 6. And now it's in the correct form. So A is 1/2, B is 5/64, and C is 6. So that was a bit more of a challenging example for you. I hope you enjoyed it. So now I've shown you how it works, it's now over to you to try these on your own. So in the book, page 312 to 313, exercise 11G, if you were to try all of the exam type questions, question 3 through to question 7, that should give you a good grounding and some confidence ready to tackle them in the real thing when it comes to the exams. So good luck, let me know if you get stuck, keep going, and I'll see you soon.